Okay. Thank you, everybody, for coming to Curry On, and especially for attending this talk. It's my first time here, so I'm quite excited. Just before we get started, can I get a rough show of hands? Who in the room is from academia? Okay, and industry? And other? Great, okay. Wasn't sure if I expected anything in that category. So, before we talk about program analysis, despite the title of this talk, I'd actually like to start from some common ground. So let's look at some code. Let's see if this clicker works. Nope, my laptop's difficult. Okay. So I'd like to start with a bug. Take a minute to look at the C code on the screen. It's part of an imaginary web application. And given that it's quite incomplete, there could be many things wrong with it. But does anybody spot a bug with this to begin with? Feel free to shout it out.
Malloc could fail.
Malloc could fail? Cool. Any other bugs?
Relationship between maxbuf and current length. I mean, if current length is longer than maxbuf, you probably have a problem.
Right. So if the length parameter is longer than what we've allocated, we could be reading beyond what we've allocated. And if it's shorter than what we've allocated, something else could happen. So with this code, we could leak uninitialized memory in the body of our response, depending on how this is handled. There's a few other bugs that could happen here as well. For example, we might never free this data. We don't have context for this code. If we were playing the role of a program analysis tool right now, we would need much more context from the rest of the program to be able to say if this is a bug or what the bug is. There are many things wrong with this code, and there's many wonderful papers finding novel ways to detect what's wrong with this code here and over the next couple days at eCoop. The space of solutions is huge. There's SAT solvers, there's taint tracking, there's control flow analysis. There's a whole bunch of interesting talks that I'm looking forward to attending. And for the purposes of this talk, they're all great. They all work to our ends. But how do we know they're great? How do we know which approach is most suited to the bug we're looking for? So all of these examples are maybe a bit facetious because they're all different languages, they're all different tools. So I want to take that example and pivot to a language where there's fewer analyses out there to choose from and see if we can figure out how we know what to build. So a language that's maybe much less classic than C and Malloc, but a similar bug exists in Node.js. What happens in this code when the str variable is not a string? Anybody familiar with this API? Yes, if it's a number, it allocates that much memory uninitialized. This API has been deprecated, but JavaScript developers did not expect to have to deal with uninitialized memory. So applications, any web application written in JavaScript, using any module with code like this could be leaking secrets to attackers. So I've chosen JavaScript for this example because it's a language with many fewer program analysis tools. So how do we choose which approach to use? Do we look at use-def chains? Do we build taint tracking? Do we just look at types? Do we just look lexicographically for this API? It's also got a very active community of developers that we can study. So that community, screenshot here from HackerOne, which is a bug bounty platform for those not familiar with it that connects companies and hopefully white hat hackers who want to report vulnerabilities. These are the top reporters of vulnerabilities in third-party Node.js modules. So we did a manual review of 609 JavaScript vulnerabilities from the Node Security Project dataset as of August 2018, before it was purchased and made private. And we found that the lower bound on the number of those vulnerabilities that were reported using automated tools is 61%. And the upper bound for how many vulnerabilities in that data set were detected with automatic tools was 77%. So I want to take a moment to recognize some particularly excellent work in this area. Liang Gong, who's now at Facebook, did excellent work at Microsoft Research on finding directory traversal vulnerabilities for Node. And Chris Staku did another excellent piece on command injection from 2017, I think. Anyway, returning to our example about new buffer, the API in Node, let's try to build a simple automated tool that will help us catch this bug. And it's not going to be the best approach. It's not going to be complete, necessarily sound, necessarily useful, but it's a starting point, and we'll take it from there. So let me see if I can get on the right screen here. Cool. Oh, I'm going to be coding without looking. OK. So can everybody read my terminal font? Should I make it a bit larger? Cool. Larger. All right. Good? Awesome. Thank you. So let's see. What we have here, I've prepared this code in advance, but there's not much to it. So these are some files that I'm going to skip over for now. They interact with our tools at R2C, and I'm not going to explain what those are for another 11 minutes if I'm running on schedule. But the program itself is quite simple. It is just a JavaScript AST walker. It consumes pre-prepared ASTs. So let me pull up the code to convince you that nothing funny is going on. Yeah, why not? Let's pull up both. Ooh, pardon my Emacs. So in this piece of code, the issue with this API, as somebody pointed out, I think, is that if you call new buffer with the first argument as a number, it will allocate uninitialized memory in that amount. And that's tricky because in JavaScript, types are not usually enforced. Modern TypeScript and other languages aside. So what we do here is we walk over an AST, we look for new expressions, and then we look at the type of the argument. So this is taking an analysis that exists already that takes a JavaScript AST and runs type inference on it, tries to let you know all of the types that can reach a certain code point. And we categorize the 3 different classes of uses of new buffer. Up, where's my cursor? OK, so up here, we record uses that are definitely unsafe, where we know that the argument is a number. So we know that we're exposing uninitialized memory. Down here, where our analysis is not able to find, a useful type or a precise type for the argument, we say maybe it's unsafe. We don't know what's going on there. And then for this last case, it's definitely safe because we know it is not a number, and we are certain enough that it is something else, whatever it may be. And this analysis, I would just like to kick it off locally here to show you that it works. So why don't I actually, yeah. So I've taken the liberty of cloning some code from 2 of the first projects involved in this vulnerability in discovering it. And I think if I just do this, maybe I ought to pipe it. This is, ignore this output. This is just build and run output. Cool. Did that work at all? Oh dear. There we go. So we have some instances in our input of definitely unsafe code. Do we have anything more interesting? Do we have any maybes? We have a maybe unsafe. And hopefully somewhere, there we go, a definitely safe. So why don't we check out bench util.js and see what's going on there. Bench util. Well, and that looks like a bug in our analysis because that sure looks like a number. Did I say definitely safe or unsafe? Oh, there's a whole bunch of usages in this file. Maybe it's referring to a different one. Yes, there we go. There's a definitely safe one with a string. So I don't know which one of these it was referring to. We'll come back to that in a bit. The important thing here is not that this is super accurate and correct for now, but that we want to get a sense of our footing. So given that we've got that output, I'm going to run the r2c push command, which will deploy this to our tools, and now show you something very briefly. Sorry, I'm not good at two monitors at once here. So, going to take that analyzer we just pushed, somewhere around here. What did we call it? Buffer leak. There we go. And we're going to pick a data set that I've prepared in advance. Oh dear, it doesn't fit on the screen. There we go. And we're going to kick that off and then leave it for now. So I will come back to that in 30 or so minutes, maybe 25, and we'll take a look. So back to our other tab. Right. Oops. You didn't see that yet. So some of you may be thinking about some problems with the approach we were taking to look for that new buffer vulnerability. Is our type analysis any good? What about buffers that are initialized with numbers but then filled with 0 data or other data to their end? That's certainly a safe case. So I want to encourage you to put that off, and we will revisit that when we can look at the data. The goal here is to be data-driven with program analysis. So earlier I mentioned that between 61 and 77% of the vulnerabilities we looked at were found with automated tools, but something we don't have a good sense of is how good are the tools? How many results did we have to look for to find 609 vulnerabilities? Alternatively, how many projects did we have to look at? Not just the precision and recall of our analysis on a benchmark, but over what size data set? How confident are we in those numbers? So what number of projects do you think is good to run a program analysis tool on to be sure in its quality and its results? People want to shout some numbers? Nobody? Anybody here write program analysis? Couple hands. Okay, what do you think is a good number of test cases? 5? It's good, set the bar low. Okay. Well, let's get 1 or 2 other numbers, and then I'll let you move on to the next slide.
Say 500.
500. One more. Somebody who writes program analysis. What? Doesn't. No good answer. I like that answer. Okay. What?
As many as you can.
Yes. So, how do we validate our research? Basically, if 61 to 77% of vulnerabilities are found with program analysis tools, then people are depending on us to make sure their code is secure, their code is fast, their code is verifiable, their code is whatever it is, or whatever they want it to be. So how do we validate our research? This is all of the papers from eCoop 2018, the conference co-located with Kurion last year, or one of the conferences, I should say. And there's one data point missing from this graph that I will explain in a second. But this is for every project that basically processed code in some way, how many different projects they looked at, not taking into account the size of the projects. So there's certainly some variance there. But most of them are around 20. There's one data point here at 76. That's GNU Core Utils as a benchmark suite. And then there was one project that sailed above the rest, looking at 10,000 Android applications. And the only reason they're not on here is because I didn't want to break the scale of the graph, and I didn't have time to figure out how to fit it. So even with 76 projects, in this case for Core Utils, what are some problems we could hit using that benchmark set to judge our program analysis? Well, one problem is that GNU-C is written in a very particular way. Maybe it's not that particular, but of all the C out there, it could be quite different. It could have code patterns, it could have stylistic choices, it could use language constructs entirely that GNU Core Utils do not use. So how do we know our analysis generalizes to these other projects? How do we know that somebody who wants to take our tools and use them is going to find anything useful? Is this good enough, basically? I hope you won't be surprised when I say that the answer is no. So this is from a recent paper on interconnectedness in the JavaScript ecosystem. This is looking at the growth of Npm packages and maintainers. And this graph is out of date because the paper was submitted in May, I believe. And the data runs through April 2018. In fact, this month, Npm passed 1 million public modules. So quite a lot of code floating around that comes from a very diverse set of developers and maintainers. So when we have, over 200,000 maintainers, and when we're installing a package, how do we know that the analysis we're using to trust code is going to apply to the package we install? This problem gets worse, too, because in any interconnected ecosystem, when you install a package, it has dependencies, and you're trusting people who write those dependencies. So this graph from the same paper looks at the number of implicitly trusted maintainers you have when installing an average package in Node. So if you install any given package in the NPM ecosystem, you are on average trusting at least 40 people with access to deploy a new version of that library. If you only trust popular packages under the assumption that they are perhaps better regulated or safer, you are trusting still north of 20 people. So this is separate, too, from committers. This is really only the people who have access to deploy the code, not just the people who write it. So just by trusting one package, we're trusting many different developer styles and patterns to run on our system, and program analysis we use to verify that may not be vetted against any of that code. And I think NPM, this won't be too controversial a statement if I say that NPM is the future, so more and more languages are starting to look like this. I'm not saying it's a good future, but I think this is the trend that we are seeing in PyPy, in other package repositories, even in Maven. There's quite a trend of exponential growth. So we as a community need to do a little better, do a little more at least, in testing and verifying our work to make it useful to people. And that's where I'd like to introduce R2C, the company I represent and work for. So we are a startup in San Francisco, big surprise. The people holding our financial whips would be Redpoint and Sequoia Capital. We are a venture capital backed startup, which means that we make no money at the moment. So that's pretty great. And this is a lot of the early team. So we hail from Facebook, Google, Microsoft, Meraki, Stanford, MIT, and I think that covers most of this photo. And we've been around for about 2 years. And the products I'm going to show you in the future slides aren't what we always were building. Like most startups, we've taken a few twists and turns to get where we are, but our goal has been consistent. And our goal is to change the way that developers write code by using program analysis. Really, we want to ensure that program analysis that measures code that has something useful or interesting to say to developers lives beyond a paper and a talk such as this. So we have tools for both average developers and for academic and industry researchers to help them do exactly that. And there's 4 primary features I want to talk about for our tools that we think help to achieve this. So one of the first features is scale. The way people do scale in program analysis presently, for the people in the room who said you're in academia, raise your hand if this sounds familiar. Do you have a cluster of 64 core machines in the basement or a closet of your university? Something similar. Anyone? Yeah. So it's not easy. It's very manual. It's very tedious. This is less relevant to those in the room from places like one of my former employers, Facebook, Google, Microsoft, etc. They have wonderful systems in-house to make that easy and quick, and sometimes I miss them quite a bit. But one thing we do is that we will bid on bottom dollar compute for you to be able to run program analysis at massive scale. So this number comes from a benchmark we did last night to make sure this demo would work. we were able to process 1.2 million commits per hour with a sort of reasonably crunchy analysis. I know that's not a sort of formal term, but just to give an idea of, we are able to execute at scale and hopefully do that for you. But there's more we do than bid on bottom dollar compute from big cloud providers. Something else we do is we have an interface that allows for pipelining of analysis components, caching results, and hosting data sets for future work. So scale is just one part of program analysis that's tedious. We also want to make it easier and faster, and our pipelining and caching and hosting services help with that as well. So we really want to reduce the amount of work that's duplicated in program analysis, whether it's compute, whether we can cache results and make things faster for everybody who wants to run similar queries in the future, or whether it's standing on the shoulders of giants. If you want to reproduce work in a previously published paper, if you want to apply it to your code, then we want to make that easier too. So one thing some of you may have glanced as I skimmed through the code on my box far away was that there was a Docker file in there. All of our program analysis tools are as unrestrictive as possible. We give you, quite literally, compute time in a container of your choosing, and as long as you understand our input and output formats, then it makes it easy to reuse the results of your analysis on anybody's system. But this also lets you create program analysis components that we can reuse, that you can publish. So if somebody wants to not only reproduce your work or dispute it, and sorry about that, but build on it as the base for future research, then they can do that. So the earlier example we ran, I talked about a component that ran a sort of reaching types analysis, and this was actually the pipeline of components that runs to do that. So there's something to acquire the source from the base specification of the data set. There's something to install the dependencies that we need for analysis. Then there's the analysis itself, and then there's what we wrote on top of it, which tries to impose some sense on new buffer. So we also support nonlinear pipelines as well. We have users doing complicated machine learning analyses that if I try to talk about, I will end up with my foot in my mouth, so I'll just leave it at that. But we support much more complex examples than this. And one thing I did not show, but we will get to, is we have a page where you can discover other people's public work and try to reuse their building blocks. So the typed AST component that I used to look at, is this call to new buffer loading an integer value for its first argument, is available on our page. There's the README, some documentation, and the buffer leak component I pushed would show up there too, and actually we'll confirm that in a little bit. So another thing we want to make easier to reuse is not just the actual work of program analysis, but data sets. I mean, one reason all of those projects hovered around 20 projects or so analyzed was because a lot of them were using the same benchmark for Java. And I forget its name, but it has something like 10 programs, and then they augmented it with a different 10 programs of their choice for each paper. Very, very difficult and frustrating. Benchmarks on labeled data sets are gold standards that are kind of hard to reproduce, and there's not a lot of incentive to create more of them. So another feature we provide, this is a screenshot of one of our data inspection and labeling tools for collaboratively producing data sets. So if you've run an analysis like that buffer analysis and you want to see results across many different projects, catalog your false positives, your true positives, your false negatives, your true negatives, and use that to not only gauge the value of your analysis, but to guide future improvement, then you can do that using this tool collaboratively. You can invite undergraduates, you can invite entry-level engineers, or you can invite your friends and whoever's rushed before your paper deadline to help you label all your data and decide what to do next. We also display context in this tool, so there's not a lot of it here, but for example, one thing we could display is if you have call graph data, say you have observed stack traces from running a test suite in another analysis, then you could use that to help you choose, is this result valuable? And if so, what do I need to do to improve my analysis? So all of these data sets, all of these input sets and analysis components, not only do we want to be shared, do we want them to be open and public, but we also allow you to take them off our system. So in this tool, you can see in the upper right, you can download the labeled data sets you produce. Our analysis doesn't require you to run on our tools. It's all open core, and it's all collaborative. But all of this is to bring us back to the question, how do we validate this research? It's great if we have tools to do it better, but what's actually important to what we're trying to do? This is where our sort of final feature and final goal comes in. We believe we have to validate research with the community that's affected and in need of the results. So developers often don't use program analysis. There's actually a great paper out of Microsoft about some of this. Chris Bird and Maria, I am forgetting her last name. Anyway, what developers want and need from program analysis. Great paper. But why don't developers use program analysis? One of the challenges is that all of the frameworks out there are difficult to deploy and use. They all have their own requirements. They all have their own formats. And even if you finally get them integrated with your editor or your continuous integration, they don't keep up to date with the language, the community, the work you're doing. One way we help with this, for example, is one of the components we've published on our system is transpilation to help you keep your JavaScript analysis current, though we aren't JavaScript specific. But back to how do we validate results as things that developers care about? You could look at developer adoption if you measured actual deployment and usage of these tools across repositories, across build systems. You could look at historical trends in code. So you could look at, do people often migrate away from this thing I'm calling bad? Or you could look at vulnerabilities. That works great for security-focused suggestions, but not so much for, you should refactor your code. But how do you really validate with developers what you're saying to them? Well, the way we got here was from a different product. Earlier in our life, this is what we built. It's defunct, so don't bother with that website. But it was an integration featuring program analysis written in-house. It was helping people vet code across ecosystems. So we incorporated social signals, program analysis, and other context, alternative things they could do, both at a glance and detailed for the code level. So this is an example of some findings we would suggest to people about code. And as we added program analysis to this tool, we learned that not only are the sort of universal problems of program analysis important, you want accuracy, right? You want low false positives. You want suggestions to be actionable and useful, otherwise they should be automatic. But you also need large labeled data sets to gauge your performance and improvement. Then you can refine analysis by incorporating classic results like reachability, or you could filter out by the purpose of the code. Is this only reached in test cases? Lots of room for improvement. But we didn't want to reinvent the wheel. We saw that all of these components exist. And furthermore, developers wanted their feedback about whether something was useful to reflect the things we showed to them. So there's an excellent study on developer feedback for program analysis done at Google. It's called Tricorder. Is anybody in the room familiar with it? Cool. A few hands. So Tricorder is great because it allows many people at Google to deploy, ranging from simple greps to slightly more advanced static analysis, checks that they can suggest to developers. And the team is pretty ruthless about making sure they stay high signal. So as soon as developers give feedback that they're not useful, they're pretty quickly turned off until they're improved. So it's helpful for the people writing these checks to see where developers reject their checks. They essentially get free labeled data from developers. Our Chrome extension product I showed you previously was our last iteration, but what we've been working on recently and is coming soon is a developer-focused integration for all of the other work happening on our platform. So when I say all of the other work, the way we ended up where we are now is we were trying to add more and more program analysis to this product, and we'd emailed several lab groups about extending their work, and they ended up being excited by the tools we had and sort of wading through neck-high mud to be able to use them. They waited weeks for email responses to get data. They put up with people like us. It was a rough time for everybody. But we realized that the tools we'd built to answer these questions and get feedback were useful to other people. So these days, we have collaborators at many different universities. I want to briefly apologize for the logo vomit that's about to happen and for violating all of the branding guidelines of the universities and companies involved. So this began with Virginia Tech and TU Darmstadt as users of our tools before we built them to be used by other people. I want to thank especially Jamie Davis, Chris Steku, Marcus Zimmerman, and Michael Prodl. I don't know if any of them are here, but they were sort of both very patient and very helpful in helping us decide to make this open. And then in January, we started building these interfaces that I previewed and that we're going to revisit in a moment to offer to anybody doing program analysis research. So now there's many more than those two groups on here, and we support them in a couple ways. So we sponsor program analysis projects with free compute and access to our tools. People are doing all kinds of things from very traditional, deep, formal verification to data mining at the most simple level to complicated machine learning pipelines that, again, if I try to describe them, I'll end up with my foot in my mouth. We also support several graduate classes at different universities teaching program analysis and empirical software research. And we've used it ourselves. For the publication I had graphs from previously was in collaboration with TU Darmstadt, and we did some interesting things for them there. So for example, we built a call graph for the entire JavaScript ecosystem, though it didn't make it into the paper. We measured code churn across all of NPM, and we looked at adoption of different libraries and different programming styles. So we also have some upcoming future collaborators, which is where even more logo vomit comes in. We are sort of in progress with all of these universities and companies and hoping to work with them. If they aren't too offended, I've put their logos up here. But it's really, as they get data, we need to start moving to getting them developer feedback, which is why that product is upcoming. So speaking of being data-based and getting data, I want to come back to the analysis we kicked off a little while ago. Let me see if I can just switch tabs. So we ran our buffer leak detector across 172,000 commits. Oh, wow, it just finished. That was good timing. I didn't plan that well. This is only the second time we've rehearsed this. And if we look here, we can see results for all of the projects and all of the commits. This data set we've prepared is 1 commit per month for every NPM project with a Git repo for 9 years, or as far as is available. And we can actually click here quickly to download some of the results. That's a boring one. Or look at the command line logs. Also boring, because we didn't add any command line logging. We can inspect where we had crashes, whatever happened here, or where one of our dependencies failed to prepare its input, so the type analysis failed on, looks like, roughly 9% of these commits. But more interestingly, we can go to some of the other things. There we go. Some of the other tools I previewed and show that they're not just screenshots, but I am going to have to zoom out a little more. Oh, no, that's not right. That's not right either. Oh dear. Well, you can see that they're not just screenshots, but they don't work very well on low resolution projectors. So we can look at, for example, the natural node project, see that we had 4 results, and ignoring the startup code and the broken UI, sorry, we can flip through the code to see that, yes, this looks probably okay. It is definitely unsafe in that it exposes uninitialized memory. However, it then fills it to exactly that length. Or does it? No, it doesn't. Actually, that's quite unsafe. If anybody's looking at this code, I'm in presentation mode. I'm not paying enough attention. So we could label this actually unsafe or something else. And we could provide comments on that. We could provide other annotations. It's not limited to true positive, false positive, but whatever you and your group are looking to prove about some code, here's your chance to put your money where your mouth is and show it with data. So we can move on. That one looks, oh dear, that one also looks funny. Wow, well, I struck gold because I chose this project at random, and the rehearsal did not go this well. So what did I call it? Actually, and you can see that our label database is slow to update for search. We're still a startup, work in progress, so let's call it actually unsafe again. Oh dear, dash versus underscore. Well, some minor engineering improvements aside, can we get a result that isn't actually unsafe? What is going on here? I don't trust this project. We're going to go back to a different project. Okay, and let's see. Got a couple minutes? How am I doing on time? Cool, great. So PDF to JSON. Oh, that sounds funny. Well, that looks definitely safe because chunk is not a buffer. No, it doesn't. Well, this demonstration just proves that everything in JavaScript is awful, which is nothing new to any of you. But this would help us refine this tool to produce actual useful suggestions to developers of these libraries. Clarifications of actually unsafe aside, it's clear we need to know who's calling this function to say when this is and isn't safe at the very least. And let me just do a little more proof of work to show you that we did what we said we did in the amount of time we did it. So there were 172,000 commits. I'm going to connect to a database with a great default password. Don't try to connect to this database. And let's see how many results. Count 8. We have from that analysis, result, no tab completion. Okay. Okay, so we have 316,000 results across the 172,000 commits we ran on. Result is single finding in code in this instance. And if we want to see how many of those were, say, definitely safe. What did I call it? Definitely safe buffer? Yes, cool, I even got the name right. So a little more than half of those are definitely safe, meaning we think we can prove that it's not a number, whatever it is. So that's just a start. Here's where we can easily, in the span of a 40-minute talk, run an analysis, gauge some data, and figure out what we need to build next to make it actually useful to a broad community of developers. What we actually do next to improve this is beyond the scope of this talk. There's many things we could do. If we found that most of the problems were in test cases, we could depend on some other components in the R2C system to look at what is test code and what isn't based on either modeling of test frameworks, dynamic analysis, etc. We could look on, we could do sort of intra-procedural data flow, or intra, I always switch those words. Anyway, it's beyond the scope of this demonstration, but before I sort of wrap things up and move to questions, I do want to just take a minute to thank some people who really helped. So I want to thank Drew Dennison and Brendan Go, especially at R2C, for staying up late and working lots to help make sure that this demo wouldn't crash. And not only that, but it finished creepily on time. I want to thank the rest of the R2C team, and I would like to thank Heather Miller and Jan Vitek for sort of allowing me here. And I'd like to thank all of you for coming. So if there's any sort of questions, I'd be happy to take them, but oh, I'm not on the presentation. Give me just a moment. there's any questions, I would be happy to take them. I'd also like to just leave on the screen my email in case you have any questions, in case you're interested in taking your research and using our tools and our free compute. And I'd like to leave a link up for our documentation. Our website is r2c.dev, where you can, I think, join our platform and get started. GetR2C.com will take you to our documentation where you can see a much sort of shorter, simpler example to run in 15 minutes to measure a moderately interesting property. So thank you very much.
You mentioned your tools are not just JavaScript specific. Have
Yes.
you tested on any other languages? And do you do any kind of binary analysis?
The one thing we have not yet approached is binary analysis. We are source specific, I should say, because our goal is to get developer feedback, and we don't yet have a clear path for how to do that for, well, binary analysis. However, we are working, hopefully, coming soon, with a group that did some really interesting work with Soot, finding duplicate code across Maven, which is somewhat binary based. So there is room forward there. We do work with Java and Python as well as JavaScript, and other languages you may have to do a little more legwork to get up and running, but we're happy to support them.
Hi. Thanks for the talk. Could you elaborate a little bit on the pipeline? So let's say I write a static analysis pass. How can I integrate it into your tool, and how do I report the results, and how does it work underneath a little bit, the implementation? So
Yes.
how can I combine it, everything?
Yes, great question. I may have to gloss over some of the details, but I can at least give a preview. So the way you interface with our system is 2 files, and that's it. Oh, that's not a good set of colors for highlighting. I hope everybody can read this if they want to. Anyway, there's a manifest file that lets you declare the dependencies you have in our system to compose your pipeline. So if there's other components you've written, you can depend on them here. We try to keep everything deterministic because it makes things a lot faster. And lets us cache a lot, so you can depend on an exact version of that analysis. We do have a couple different types for if you want fan-in or fan-out aggregation at different stages. And the way you actually sort of take your analysis tool and your path and integrate it with our system is you just put it in a Docker container, and whatever entry point you'd like, your code just has to understand where its inputs and outputs are, and we support 2 types of outputs, and then the input corresponds to what you're depending on, what its output type is. So JSON output is our format, which has lots of escape hatches for arbitrary data, but the more structure you provide, the more it integrates with our other tools. And then we support arbitrary file system output for, say, large binary output or intermediate transformations of a program.
Thanks.
Questions? All right, well, if anybody has any more questions, you know where to find me. And I will be around all week for both Kurion and eCoop. So thank you, everybody, for coming, and see you around.